Very good evening to all respected members. I welcome all the members to day 3 of our faculty development program on robotics. Today's session focuses on motion programming and path planning, one of the most important aspects of industrial robotics. We will learn how robots are programmed to move accurately, efficiently, and safely while avoiding obstacles. By the end of today's session, you will understand how motion commands are converted into intelligent robot movements for real world applications. Let us begin our today's discussion. Now we will go through the program agenda at a glance. Today's program comprises of 4 sessions. We begin with fundamentals of robot motion programming. Next, we study the basics of path planning. Then we explore classical and modern planning algorithms such as Dijitra's algorithm, A-star algorithm, rapidly exploring random tree algorithm, and the probabilistic roadmap algorithm. So these are the set of algorithms used for path planning operations in industrial robotics. Finally, we conclude with the basic simulation exercises and key learning outcomes. Next, we forward to the learning outcomes of day 3 faculty development program. At the end of today's program, you will be able to program robot motion using point-to-point, linear, and circular motion commands. Differentiate between global and local path planning approaches, understand and apply common path planning algorithms, generate smooth robot trajectories using velocity profiles. Finally, relate these concepts to industrial robots, autonomous mobile robots, and automated manufacturing systems. So the next phase we are going to discuss about introduction to motion programming fundamentals in industrial robotics. Motion programming refers to instructing a robot on how to move. It specifies the robot positions, orientations, different motion types, speed, acceleration, and sequence of operations. Motion programming bridges the gap between planning and physical execution. Accurate programming improves precision, repeatability, productivity, and operational safety, making it essential in welding operations, assembly, painting, and pick and place operations. Let us now classify the different types of robot motion according to the existing literature survey. There are 3 commonly used robot motion types. First one is point to point motion. It moves each robot joint independently to reach the final destination quickly. Linear motion ensures that the robot tool moves in a straight line path. Circular motion allows the robot to follow a smooth curved path through specified points. The choice of motion depends upon the application of usage and accuracy requirements. So here are certain the motion programming languages as listed below. ABB robot use rapid simulation motion programming languages. KUKA robot use KUKA robot programming language. Fanuc uses teach pendant programming language. Like that, there are many other simulation the programming languages that are used for motion control programming in industrial robotics. Now let us discuss the foundations of path planning. Once robot motion is defined, The robot must determine how to reach the destination safely. This is called path planning. The path planning algorithm identifies most feasible route from the starting point to the target while avoiding obstacles and satisfying the robot constraints. It forms the foundation of autonomous robot navigation. Next thing, we will try to understand the discrimination between global and local path planning. Path planning is broadly classified into two major categories. One is global planning, assumes a complete map of the work environment and computes an optimal path before movement begins. In contrast, local planning reacts to sensor information during robot motion and avoids unexpected obstacles in real time. Industrial robots often combine both methods for efficient navigation. Classical path planning algorithms. Next phase, we are going to discuss about the list of classical path planning algorithms. There are two widely used graph search algorithms are Dijistra's algorithm and A-star algorithm. Dijistra's algorithm explores every possible route systematically to guarantee the shortest path. A-star algorithm enhances this process by introducing a heuristic estimate towards the goal, making it more faster while maintaining optimality. These algorithms are widely used in warehouse robots, factory automation, and logistics systems. Next one, we are going to discuss about sampling-based algorithms. For complex robot systems with many multiple degrees of freedoms, sampling-based algorithms becomes more quite effective. There are two methods. First one is rapidly exploring random tree algorithm randomly explores the search space until a feasible path is found. Probabilistic road maps. It tries to build up a network of collision-free path and search for the best route. These methods are especially useful in robotic manipulator and autonomous navigation. Next method is artificial potential field method. The artificial potential field method is inspired by virtual forces. The goal creates an attractive force that pulls the robot towards it. Obstacles generate repulsive forces that push the robot away from the obstacle. The robot continuously follows the combined force field towards its destination. This method is computationally efficient and suitable for real time navigation, although it may occasionally become trapped in local minima. Next method is trajectory path planning. Here, a path specifies where the robot should move. Trajectory specifies how and when the robot should move within the workspace. Trajectory planning defines the position, velocity, and acceleration throughout the motion. The trapezoidal velocity profile is one of the most widely used profile because it provides smooth acceleration, constant speed travel, and controlled deceleration, reducing vibrations and improving positional accuracy. Let us now discuss the real world application of motion programming and path planning. Industrial robots use these techniques for welding, assembly, painting, and material handling. Automated guided vehicle and autonomous mobile robots navigate warehouses efficiently. Autonomous vehicles rely on intelligent path planning for safe navigation. Flexible manufacturing systems continuously adapt robot paths to changing production requirements. Every successful robotic application combines planning, programming, and smooth trajectory execution. Let us discuss hands-on laboratory, a practical session. I'm leaving this particular segment to every students and faculty members of various engineering colleges. Probably your institution may have a resource facility called simulation lab. So whatever the robotic simulation package available in your institution, using that you can able to generate a program for point to point, linear and circular robot motions. implement A star and RRT algorithms within a simulation environment, generate trapezoidal velocity profiles, finally, discuss the observation and identify the industrial application for these concepts. So, this practical session reinforces the theoretical knowledge gained today. Let us now discuss some few simulation illustrative example by through video presentation. So we will resume back to the normal PPT mode presentation. So we have seen a practical illustrative simulation lab for industrial robotics. In this particular application, we saw about autonomous quality control inspection check for a finished manufactured part with the help of pick and place arm type industrial robot manipulator. So here we might have witnessed the different motion commands like point to point, linear, and circular path motion. So like that, you develop a simulation exercise in your workplace where you are located and try to understand the basic mechanisms by implementing the following algorithms like A star and RRT algorithm within that particular simulation environment. So let us wrap up the today's learning journey. So the motion programming converts the robot instructions into executable motion movements. Path planning determines safe and efficient routes. Trajectory planning adds timing, speed, and acceleration for smooth robot operations. Together, these concepts enable intelligent robotic systems used in manufacturing, logistics, healthcare, autonomous vehicles, and smart factories. So, finally, I thank all the members for your active participation. We will meet in the next day 4 faculty development program on sensors used in industrial robotics. What are the various input and output interfacing systems? So we will discuss in the day 4 the next subsequent faculty development program.